Okay, so I'm very happy to introduce Eugene Kirpichov, staff software engineer at Google. Eugene is currently working on machine learning and optimization and making machine learning and optimization a first-class citizen in application programming. And he also spends nights and weekends volunteering on ventilator projects to make ventilators for COVID-19 patients. If Eugene wasn't in the predictive analytics field, he says he'd want to work in climate change mitigation, which is an interesting topic too. So thank you, Eugene, for sharing your vision with us today. I'd like to remind the audience to put questions into the chat box at any time. I'll pop on, I'll leave the session, and I'll pop back on at the end to read questions.
Sounds good. Then I have 17 minutes for the presentation and a few minutes for questions, right?
Yep. And since we're starting a little early, we should have a few more minutes for questions.
Okay,
all right.
Great. Then I guess I'll get started. Okay. Hi, everybody. I'm Eugene. I work at Google in research and machine intelligence. And in the past couple of years, I've been working indeed on making machine learning and optimization a first-class citizen in application programming. And that's what I'm going to be talking about today. First of all, a little more about exactly what I work on. It is a project called Smart Choices. And there is a paper on arXiv about exactly what it means. But basically, it's a library or service that makes choices for you. It makes heuristic choices for you. It makes choices in context. So for example, you can ask it to choose how many threads you want to use for running this parallel query, or like in a more general case, which ad to show for this page. One of our production customers, for example, is Google Flight Search that indeed has a bunch of very heavyweight combinatorial search queries, and they use us to decide how many threads to run them on. And the pseudocode for that is very simple. You ask us to, you declare a choice, you ask to choose, it gives you a number or some other option, and then you use the number and you tell us how well it went, and over time this improves by learning a model in the background. This is called a contextual bandit, which is the simplest form of reinforcement learning where you only make one action. More generally, of course, we're working towards more than just contextual bandits. We want to make ML-augmented programming like an everyday thing. We want to make learned functions as common as regular functions. And let me tell you what I mean by ML-augmented programming. I mean by that, this is software where some parts of it are learned towards a goal as opposed to just hard-coded. For example, you could imagine that a cache might have an eviction or admission policy that decides which keys are more important, and it admits important keys and evicts unimportant keys. There can be a few advantages to this approach. First of all, it can give better quality than any heuristic you can possibly code, because perhaps the best heuristic is more complex than a human can code. Second, somewhat surprisingly, it can end up being more maintainable. Hand-coded heuristics or tuned parameters tend to rot over time. Basically, anytime you see a parameter set in code, it's almost certainly out of date, or quite likely it's actually harming the system, because right now the value is not optimal anymore. But this is not the case if the system learns the heuristic itself. As for whether it's cheaper overall, no, there is no free lunch. Usually it is not cheaper because even though the decision-making itself, you can just delegate it to a model, architecting the system so that you have somewhere to plug a learned decision turns out to be surprisingly difficult, and I'll talk about this later. Let's see how our project went and what problems did we face. We worked with close to 100 teams all around Google and tried to solve problems such as learning caching policies or deciding which Chrome tab or Android app to kill on memory pressure, when to send what kind of notifications, all kinds of stuff that seems like it should be low-hanging fruit for ML. Meaning that you should be, maybe making the optimal model is hard, but doing better than a hand-coded heuristic seems like it should be easy. The outcome of that is that we have a few clients in production. A few more are kind of within reach. We know how to do it, but we just haven't done it yet. But the majority of them turned out to be way harder than we thought. And I spent a lot of time thinking why it is so hard, and this talk is what came out of it. You basically hit difficulties every step of the way trying to introduce a learned heuristic into a program. First of all, turns out that most problems that you want to solve, they're not textbook. They're not regression. You're not trying to just predict input from output, output from input, I'm sorry. They're not a bandit problem because you cannot tie a metric directly to a single decision that caused this metric. It's not reinforcement learning because the decisions are not sequential. For example, you're making lots of decisions in different threads in parallel. Oftentimes, the problem is too messy. Like maybe the behavior of the problem is non-stationary and the only training methods you know only know how to deal with stationary problems. Or decisions are non-independent. Maybe it converges only some of the time. Maybe you need so much hand tuning that it's more trouble than it's worth. Now, if you can pick a method that can work, the next step is wire it up to the system. And then you hit the barrier that features and reward metrics are inaccessible programmatically. For example, maybe the metrics, maybe you're making the decision in some low-level library, but you're trying to optimize some high-level system objective, and it's just a violation of abstraction to even know that that objective exists. Or maybe the feedback is defined informally, and nobody can quite tell you what it actually is. They just want the system to be better overall. Of course, you can't programmatically optimize for that. And then if you get past this, then you hit troubles when trying to roll it out. Basically, nobody simply wants to optimize latency or increase clicks. Everybody has much more complex criteria, and oftentimes the criteria are, again, informally defined. And basically, people cannot trust rolling this out automatically to a machine. They want to look at every change, and that kind of defeats the purpose of continuous learning. So is it hopelessly hard? I hope not. But basically, the problem we're facing is that we have a bunch of really impressive ML methods, but they are kind of narrowly applicable to only particular classes of problems. And we have problems that look easy for ML, but they're too messy to actually go ahead and apply well-known ML. My gut feeling, though, is that we can succeed here because most of the problems we're talking about, they're not unsolved. They're just nobody has tried to solve them because, surprisingly, there have been very few attempts to make ML a part of everyday programming the way that we're trying to. So nobody has quite hit these problems. So the goal of this talk is to discuss how we can solve this. And I'm hoping that we can come out of this talk with a shared vision of how a end-to-end programming stack can look like, where machine learning is an application programming primitive rather than like something to the side of it. Let's talk about this. I like to think about how this can be done in terms of these 7 layers, with just regular everyday application programming at the top and machine learning mathematics at the bottom. The top layer, application programming, is mature enough that we don't need to talk about it. Mathematics and modeling libraries like TensorFlow are very impressive, but as we will discuss, they are unfriendly to building abstractions on top of them. And then there is a big part of the picture, which is a few layers that just don't exist, but I think are a crucial component of this vision. There is repackaging machine learning as a primitive in application programming. So, for example, just having a C++ library that can do contextual bandits or optimization, as opposed to having to use a separate service for that. Then there is what I would like to propose as a, new field of computer science, which is ML-augmented algorithm design and programming language theory. How does machine learning interact with software design principles? The same way we talk about how to decompose code into functions, how do we decompose code into learned functions. On top of that would be a layer of smart libraries, which are libraries that perform kind of everyday tasks, for example, caches, load balancing, allocators, thread pools, but with learning integrated into them. And of course, they would have to be wired with the rest of the system in terms of features and rewards. And on top of that is another layer, which is system-level optimizability, which is how to architect systems that can be optimized in principle. If you have an optimization method, how to make a system that can use it. We'll talk about all of these in detail from now on. So the focus of this talk is on the problematic layers. Let's go through them one by one. From the bottom layer of machine learning mathematics, the problem with that is that modern machine learning happens to be very unfriendly to building abstractions on top of it. All the abstractions are leaky, meaning that they kind of can do what you want, but there is a big caveat. For example, deep neural networks can recognize images, but only if you give them just the right hyperparameters, or the model will only converge 80% of the time, or you need to own and manage and administer a GPU cluster to do that. Basically, you can use this directly and get impressive results, but you can't build an abstraction on top of this. For example, imagine that garbage collection had caveats like this. You just wouldn't be able to code in Java or anything of that sort. So we need to increase the part of ML abstractions that is suitable for use as a building block as opposed to just direct use. The way we can do this, I think, is by incentivizing things that are friendly to abstractions. We need to stop asking ourselves about ML methods. Do they beat state of the art on individual benchmarks? Because this kind of incentivizes one-trick pony methods that solve one problem impressively well, but you can't do anything else with them. And instead, we need to start asking, does it just work? Maybe it doesn't work quite as well, but it works all the time. Is it safe? Does it converge all the time? Can it handle non-stationarity in the problem? Is it cheap enough? Do we need to hand tune it? And so on. I think the way that as a community we can achieve this is by creating the right incentives. For example, I imagine we would need something like a Kaggle, but for abstractions rather than individual problems. You could imagine a benchmark where a bunch of problems are pitted against a bunch of methods, and for each combination, you simply get a pass-fail. So you cannot squeeze fractions of a percent, but you can strive to solve more problems without tuning. And the crucial part here is that you would not be allowed to change anything about the code or tuning between different problems. I think if we had something like this, it could spawn a new wave of research into methods that achieve this, such as AutoML that converges quickly and easily, even if perhaps with not quite as impressive results as more heavyweight AutoML, methods for boosting this kind of just working properties of existing methods, and so on. Now, if we were able to get our math straight, we would be able to create a new field of programming language theory or computer science on top of that. And I'm hoping that one day we'll see books like this. We'll see the theory of algorithms and design patterns for ML-augmented software, where parts of it are learned rather than hand-coded, including analysis and best practices and so on. I think this is basically a clean slate. It's exciting, and it's kind of like data processing was before MapReduce was invented. And there is a lot of areas to this, and it is well worthy of being a new branch of computer science. There is different primitives like regression, bandits, optimization, control theory, and so on. You could think of ways you could compose models and compose their goals for optimization. You could think of ways that models can be reduced to each other. You could think of completely new things that don't exist in regular algorithm analysis and the way we write code usually, such as simulation gyms where you train a model, transfer learning, and so on. So I think this is really interesting. Now, if we got that stuff together, then we would be able to build smart libraries. So libraries that do everyday tasks, but more smartly, using machine learning under the hood. And you could imagine these libraries existing everywhere along the software stack, from high-level libraries such as caching, load balancing, auto-scaling, parallel processing workloads, and so on, to middle-level libraries. For example, it turns out that remarkably often you need to decide how to break a stream of events into batches for batch processing. Or maybe you want to predict the time when an object will next be accessed. Or maybe you want to predict how big is an object so that you can prepare your sources in advance. And there could also be libraries at the lowest level, such as smart data structures, allocators, thread pools, and so on. And the layer on top of that, if we had these libraries, we would need to be able to wire them into a system. And for that, we would need the system to possess the trait of optimizability. And I think eventually in a few years, it will play a similar role that testability plays in modern systems. So it is a system that is amenable to being automatically optimized. And you can think that such a system should have a learning plane, like some systems have a control plane and a data plane. An optimizable system should have a learning plane. And what happens on that plane is that certain knobs or heuristics are being continually tuned towards goals. And the tuning happens via actuation. So the learning system decides what values of the knobs to try, and it actuates them, supposedly safely and granularly, and rolls back bad choices. And then the system computes how well did these settings perform and reports back to the learning system. And this loop continuously runs, and the system just gets better over time. And I think this could be not just an architecture pattern. You could imagine that if a system exposes this through an API, for example, if a system exposes some sort of manifest of what aspects of it are tunable and what are its goals and constraints, you can imagine having a self-tuning cloud in which you run systems of this sort, and the cloud tunes them for you. So let's walk through all of these layers on an example of learned caching. At the level of application programming, the only thing you would notice is that your cache cluster works better and seems to adapt better to unforeseen workloads. This would be possible because your system is architected in a way that it is optimizable, meaning it has metrics that are available programmatically. It exposes its constraints programmatically so that the smart caching libraries can access them and optimize for them. And your actuation of proposed new caching policies is automatic, granular, and safe, meaning that if you want to try out a new caching policy or several of them at once, there is a way to do that granularly enough that you don't set your whole system on fire if the learning produced something that is not actually safe to use. This would be built on a foundation of a smart library for caching developed by caching experts rather than ML experts, thanks to the work of layers below of exposing ML in a way that can be programmed against. This library would likely have an API where it observes cache hits and cache misses and decides what to admit and what to evict. It would have to be customizable with features of your keys that would be system specific, and it would have to have its optimization goals wired up with your system's high-level optimization goals. These libraries, in turn, would be built on a foundation of best practices and methods of analysis of ML-augmented algorithms. It would be designed according to best practices and patterns for what should the API of learned libraries be like, how they should be tested, how they should be deployed, and so on. It would be decomposed cleanly into primitives. For example, you could imagine that the problem of cache admission and eviction can be reduced to a problem of regression, basically predicting how long an object will stay needed, or perhaps when is the next access to the object going to happen. And we would be able to analyze the convergence behavior of these models and how much quality we can expect from them. And this, in turn, would be built on a solid foundation of abstraction-friendly ML mathematics, mathematical methods of ML, such as online learning, a system that can learn from a continuous stream of training data, AutoML that can work quickly and doesn't require a gargantuan amount of resources to train, even if perhaps it doesn't give you the absolute best result. Methods for improving the safety of existing methods. For example, maybe you can mix this learned policy with a regular LRU caching policy in a way that you can guarantee that the overall thing is not worse than LRU. And this is actually something that our project Smart Choices does. And all of these methods would be developed thanks to the incentive of building methods that just work. So probably none of these methods would be winning any single benchmark, but they would be winning benchmarks on how many problems they can solve just out of the box. So people who invent these methods would be rewarded. That's about it. I would like to finish with a call to action for engineers and for researchers. For engineers, I would like to encourage you to build your systems with optimizability in mind. Imagine that your system, that one day there is going to be something that can tune your system if you let it. For that, your system needs to have a learning plane, the key components of which are clear optimization goals and constraints that are not human defined, that are programmatically accessible and rigorous enough that if your goals go up and your constraints are not violated, then you trust the result. And you need your system to be able to safely and granularly actuate changes to these heuristics and policies. If that's the case, then your system is in good shape. And if you're a researcher, I would like to encourage you to build methods that are friendly to abstractions. Emphasize the ability of a method to just work over best case performance. And I think we need something like a Kaggle, but for ML abstractions. I have actually talked to people from Kaggle. They seem to think it's a good idea too. It hasn't happened yet, but basically I'm not alone in thinking this. And if you're an ML researcher or a programming language theory researcher, I think you have a lot of interesting stuff ahead of you if you start investigating what can be done in the area of ML-augmented software design. Meaning, how can you compose ML models and compose their goals and analyze their learning behavior of their compositions and reduce one problem to another and so on. So this is about it. Thank you. I would like to take questions.
Thank you again, Eugene, for sharing your vision with us. Are there any, please audience, put your questions into the chat box if you have any. And while people are typing in, I was wondering if you could just kind of comment on the question of robustness, the just works concept. I know obviously we're all facing a new situation with COVID and its impact on our models. How do you think that your ideas sort of would these actually help address that kind of challenge?
Are you talking about whether the ability to just work would help us with COVID models?
Well, not models of COVID, but all of our models that are based on historical data are currently in question.
Oh,
we're in a sort of a crisis point. Yeah. So do you think that some of this would be applicable to sort of making our models more robust to shock events like this?
Yeah, yes, absolutely. This is very similar to actually questions we've been asking ourselves when trying to optimize certain just high performance distributed systems. So you want, for example, if you're doing caching, you want not just to cache well in the common case, you also want to cache well if something in the world changes and your traffic pattern is completely different. So anytime we approached the user-facing service team, they asked us like, how about this? What are you going to do? And that is why we developed the safety devices that in some special cases guarantee that we're not going to be more than a certain fraction worse than the baseline. So this is possible. It's not too hard, and yes, it's a very valid problem to attack.
Safety measures level of the stack again. Do they go in? Are those part of the libraries or the primitives?
I think they probably go partially in the math. It's basically meta bandits. Like, but if you have two models, how do you make a composite model that doesn't know worse than either of them? And one of the models is a heuristic that you hand coded, and the other is the learned model that you're trying to use to improve it. And if you compose them in this way, then you got something that's never worse than the hand coded model, and sometimes better.
Cool. I like the idea of dual models because I know that that's something that's definitely an issue facing a lot of organizations. I don't see any questions right now. I do think that this is the end of the session. I'd like to end on time. So thank you so much. I'd love to hear about the Kaggle future. Thank you, Eugene. Thank you, everybody, for your attention. I've enjoyed, this is my first predictive analytics world, so I've had a good time. Hopefully everybody has too, and adjusted to the online format. We're getting some thanks into the comments. I don't know if you can see them, but in the comments box, Eugene.
Yeah, thank you for letting this well.
Yeah, thank you. Thanks very much. So hopefully everyone has a good evening, and maybe see some of you back for some more sessions tomorrow.
Okay. Bye.
Good night, everybody.